In today's class, we will discuss about radius of nucleus and nuclear density. First of all, we know radius is proportional to the size of the nucleus. So, if you consider hydrogen nucleus or any lighter nucleus with less number of protons and neutrons, so let us assume there are few numbers of protons and neutrons inside the nucleus, so that the size of the nucleus we can approximate as shown in figure like this. And if you are having a nucleus which is having more number of protons and neutrons, and in that case we will be having large size, or the size of the nucleus will be large, and the radius also will be large, or the volume of the nucleus also will be large. Okay. So when you compare the size of the nucleus, as you can see from these figures, this is a small nucleus and this one is a heavy nucleus. Okay, and this is based on the size of the nucleus, obviously. And the size we can also say as the volume of nucleus, and the volume will be less in the first case, in this case, and the volume will be large in the second case. So basically we can say the volume is proportional to the number of particles or number of nucleons, that is neutrons and protons, inside the nucleus. If the number of nucleons or number of neutron and proton is larger, then the volume of the nucleus will also be larger. If the number of nucleons small, or which is like hydrogen, lithium nucleus or lighter nuclei, in those cases the number of neutrons and protons will be less, and the size of the nucleus or the volume of the nucleus will be small. So basically the volume of the nucleus, volume, you can write it as volume of the nucleus is proportional to volume of the nucleus is proportional to the number of nucleons, and volume we can say it as, if you are considering it as it has a spherical structure, if the nucleus is having a spherical structure, then we can approximate it as 4 by 3 pi r cube volume, and this volume is proportional to number of nucleons. Number of nucleons is nothing but the mass number of nucleus, so we can just say it is A. Okay, so 4 by 3 pi r cube is proportional to A. What is A? A is the total number of nucleons, and that is equal to the number of neutrons plus number of protons. We denote number of protons with Z. So total number of nucleons equal to number of neutrons plus number of protons, and that is equal to mass number of the nucleus. This is the mass number of nucleus. And when you write in the symbol form, let's say you are having a nucleus X, then your mass number will be here, and the atomic number or number of protons will be on this side. Okay, now for this volume is proportional to mass number A, or you can write R cube is proportional to 3 by 4 pi will come here, okay, and this a, or you can simply say r cube is proportional to a, and r is proportional to a raised to 1 by 3. And to remove this proportionality, we put a constant, and this constant we obtained from different experimental results, and that constant is R0, and which is having value 1.2 into 10 raised to minus 15 meter. Okay, and so we can write this R equal to R0 a raised to 1 by 3. So this is the expression for radius of nucleus, and you can see the radius of nucleus is directly proportional to the cube root of its mass number. Okay, and this R0 we obtained from different experimental uh, results, and which is 1.2 femtometer. This is nothing but R0, you can write it as 1.2 femtometer, because 1 femtometer is 10 raised minus 15 meter. So this is the expression for radius of any nucleus. Okay, so if you consider any nucleus like hydrogen or uranium, hydrogen you have to put A equal to 1, and for uranium you can put A equal to 235. Okay, so depends on that the radius will be different. So if you consider hydrogen atom, then you'll be having mass number that is equal to 1, and then if you put that value, then your R will be equal to R0 a raised to 1 by 3, that is 1 raised to 1 by 3. And that will give you the same result. Similarly, if you consider uranium, let's say uranium 235, then in that case you have mass number A equal to 235, and your radius of uranium nucleus will become R0, that is 1.2 into 10 raised to minus 15 into A raised to, that is 235 raised to 1 by 3. So if you calculate this one, then you will get what is the radius of uranium 235. So depending on that mass number, each nuclei will be having different radius. Okay? And depends on that the size of nucleus will be different, or the volume of the nucleus will be also different. Now talking about the density of the nucleus, if you consider density of the nucleus, so let us assume we are having a nucleus consist of number of nucleons like this. Okay. Now each of these nucleons are having mass m, and which is nothing but the mass of protons and mass of neutrons, and they are almost same. And then we can say, if you are considering the density of the nucleus, what is the density? Density is nothing but mass per volume. So if you consider the total mass of the nucleus, which is nothing but this the total number of nucleons inside the nucleus, that is A, that is the mass number. Okay, total number of nucleons in this nucleus, that is A. So total number of nucleons times the mass of each nucleon, that is M, that is the total mass of nucleus. Total number of nucleons into mass of individual nucleons, that is the total mass of nucleus, divided by 4 by 3 pi r cube, where r is the radius of nucleus. So this is nothing but mass per volume. And then you can write this density, we represent it with the rho, and density of nucleus will be equal to, you can say this as A times M divided by 4 by 3, and this pi r cube is nothing but pi into r0 cube into A. Okay, because r equal to, and this is coming from, because r equal to r0 a raised to 1 by 3. So if you put this value in this equation, let's say this is equation number 1, then if you put this r equal to r0 a raised to 1 by 3 in equation number 1 for r, then we'll get this expression. Okay, now you can cancel these two a's, and you'll get nuclear density rho equal to mass of nucleons, that is mass of protons and neutrons. Okay, mass of neutrons, single neutron, okay, single neutron or proton, divided by 4 by 3 pi r0 cube. Now you can see this mass m is constant, that is the mass of neutron or proton, and this 4 by 3 pi r0 is also constant. So all these terms are constants. So then we can write this as you can see, this mass of neutron or mass of proton, that is equal to 1.66. You can write it as 1.66 into 10 raised to minus 27 divided by 4 by 3 pi r cube. So this is 4 by 3. Pi is 3.14 into r0 is 1.2 femtometer. So 1.2 into 10 raised to minus 15. So cube of this. So if you do this calculation, then you will get the nuclear density, and that is equal to 2.27. Write it as 2.27 into 10 to the power 17. 10 to the power 17. 10 to the power 17 kilogram per meter cube. So this is very large value. So you can see from here, this is 2.27 into 10 raised to 17. So if you consider 1 meter cube volume, then the density of the nucleus will be this much, okay, which is the order of 10 raised to 17, which is a very huge value. Okay, so density is very high, and also you can see, even if you put here if you are considering the density of nucleus of hydrogen or density of nucleus of uranium, all of them will be having same value. So which means that basically the nuclear density is a constant. So if you are considering uranium, if you substitute for example 235 here, it will be cancelled out, and the nuclear density for any nucleus, that will be constant, and which is 2.27 into 10 raised to 17 kilogram per meter cube. Now if you further consider the experimental results, then you can see the graph of nuclear density versus, I'll just draw here, nuclear densities versus radius. You plot that. Then for lighter nuclei, for example, if you consider some nucleus of copper, I will just draw that here. let's say that 2.27 will be somewhere here, and then it will be going like this. Okay. For this is for lighter nuclei, for example some copper nucleus. And if you consider another example like heavier, somewhat heavier nuclei, like say some gold, the case of gold, it will be slightly up here, and it is constant, almost it is constant, and then after certain distance it will start decreasing. So the trend is same, and this is for gold. So heavier nucleus, you are having a little the nuclear density value a little up, but it's constant, but and it remains as such for certain distance. Similarly, you can see for copper also, or lighter nuclei also, it is constant for uh, some distance, which is in this axis we are having distance. Distance means from the center of nucleus, and this side we are having the nuclear density rho. So if you plot this, then this will. So heavier nuclei, there is slight shift from this density 2.27 into 10 raised to minus 10 raised to 17, but it is almost same, and it is constant. Okay, it is constant for certain period, for a certain distance. Let's say this is constant up to, for copper it is constant up to this value, and it is constant up to this value for copper. Okay, so which means that the nuclear density is almost constant for certain distance from the center of the nucleus, which means number of nucleons inside the nucleus is same for up to certain distance, and then it starts decreasing. Okay, so at the outermost region of the nucleus, the number of neutrons or number of protons, they will be less at the outermost region, but almost at the inner regions of the nucleus, the number of neutrons or number of protons, if you take all together, that is number of nucleons, they will be, that will be constant. So for this much of range of radius or distance, they are constant. Number of nucleons per unit volume is constant, but after that there is slight change, as you can see. So which means that the nucleus is not having a rigid wall. Okay, the nucleus is not having a rigid wall. The nucleons, number of nucleons are not same as at the inner and outer portion of the nucleus. There are slight difference, so that's why this density is decreasing after reaching certain distance from the center of the nucleus. Okay, so for lighter nuclei and heavier nuclei, the trends are same, which means that the nuclei are not having a rigid boundary. Okay, now in the next class we'll do some problem based on this nuclear radius and density of nuclei.